Okay, in this video I'd like to talk about pH titrations. So a pH titration is basically when you add bit by bit of a solution for which you know the concentration, and this is either an acid or a base, and we call this the titrant, to a solution for which you do not know the concentration of an acid or a base, and this is called the titrand. So this is essentially a neutralization reaction. So if you're adding in a known concentration of an acid, for example, for your titrant, you would be adding that to an unknown concentration of a base for your titrand, and vice versa. If you added in a base with known concentration for your titrant, you'd be adding that to an unknown concentration of an acid for your titrand. And you can mix and match a strong acid with a weak base with a strong acid, weak acid with a weak base, etc. So why would we want to do this? Well, it turns out a pH titration is very useful for allowing us to determine this unknown concentration here of this solution. So remember, we know the concentration of the titrant, but we don't know the concentration of the titrand. So the first example I want to go through here is a strong acid. Our titrant is going to be neutralizing a strong base, our titrand. So the strong base is going to be 200 milliliters of an unknown concentration of NaOH. Remember, we don't know the concentration of the titrand. And our titrant is going to be 0.1 molar HCl, and we're going to be adding in 100 milliliters of that. So remember, for any neutralization reaction, the first step is to figure out what our initial compounds are going to dissociate into and how that's going to affect the pH. So we know NaOH dissociates into Na plus and OH minus. It's a strong base. And we know that of those ions, only OH minus will affect the pH, and HCl will dissociate into H plus and Cl minus, and of those ions we know only H plus will affect the pH. So we allow those two important ions to neutralize each other in the step 2, and they are going to create pure water. So we would expect that if there were equal molar amounts of H plus and OH minus, in other words, if there were equal molar amounts of NaOH and HCl, we would have a solution of pure water and then just this Na and Cl floating around that don't affect the pH. So the pH would be 7 if we have equal amounts of these two. But here's the thing. We don't know the concentration of NaOH, but we do know the concentration of HCl. So if we add in a specified amount of HCl, we can actually back calculate and figure out, if we can make the pH 7 with a certain volume, what the concentration of the NaOH solution must have been. So let me show you how you do this. So again, I said I had 200 milliliters of an unknown concentration of NaOH, and I'm going to add in 100 milliliters of 0.1 molar HCl. So if I add in 100 milliliters, that's 0.1 liters of a 0.1 molar concentration. Remember, molarity is moles per liter, so if I multiply by liters, I get the amount of moles in 100 milliliters. So when I add in 100 milliliters, that means I add in 0.01 moles of HCl. And I'm going to tell you, I'm just going to give you this information. This made the pH of this mixture solution 7. Okay, so what does that mean? That means that if we add in 0.1 molar HCl in a 100 milliliter amount, and we add in 0.01 moles of HCl, that must have completely neutralized all of the NaOH in this unknown concentration solution. So that means we must have had the exact amount of moles of NaOH. So if we added in 0.01 moles of HCl and it made the pH 7, we must have had 0.01 moles of NaOH for that HCl to precisely neutralize, because if we had any less or any more NaOH, the solution would not end up at 7 for pH. So since we know there were 0.01 moles of NaOH in those 200 milliliters or 0.2 liters, we can say that 0.01 moles of NaOH must have been in those 0.2 liters, and this is the definition of molarity, moles per liter. So we know that this solution must have been 0.05 molar NaOH. And that makes sense, right? If 100 milliliters of this solution was able to completely neutralize 200 milliliters of this solution in a 1-to-1 molar ratio, this solution must have been half as concentrated as this one, right? So that makes sense. So this is, if you were to plot moles of this solution HCl added versus the pH of this mixture solution down here, this is what it would look like. So when we haven't added any moles of HCl yet, we're going to be up at a very high pH, right? Because this is a strong base by itself. And then once we start adding moles of HCl, the pH is going to go down slowly, 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 and then it'll start picking up speed extremely quickly. And the slope will become nearly vertical. And at this highest point of slope, this is called the equivalence point. This is the exact point where the moles of HCl equal the moles of NaOH. And when you're adding a strong base to a strong acid, or a strong acid to a strong base, either way, the pH of the mixture is 7 at the equivalence point. Okay, so I hope that makes sense. Okay, in this second example, I want to talk about titrations when the titrand is weak. So remember, in the first example, our titrand was a strong base. It was NaOH, and then the titrant was HCl. So it was a strong base being titrated by a strong acid. So here the two scenarios that you have are either you can have a titration of a weak base, that's your titrand, by a strong acid, that's your titrant, or you can have titration of a weak acid by a strong base. So weak acid would be your titrand, and your strong base would be your titrant. So in this case, we've got a beaker full of weak base, and we're dropping strong acid into it. And here we've got a beaker of weak acid, and we're dropping strong base into it. So let's start by talking about this graph here. So remember, in the previous example, when we had a strong base being titrated by a strong acid, the equivalence point was right at 7. But in this case, the pH at the equivalence point is less than 7. And that's always going to be the case when you have a titration of a weak base by a strong acid. So remember, when we start the titration, we just have this jar of weak base. So the pH we would expect to be a bit basic because it's a base. And then once we start adding in strong acid, the pH is going to change ever so slightly. And then as we add more and more, the slope is going to increase until the slope reaches its maximum value at the equivalence point. And at this point, enough strong acid has been added such that the moles of weak base equal the moles of the strong acid in the mixture, and the pH at the equivalence point, as I said, is going to be less than 7. So I want to talk about a few ranges in this graph. So from about here, after you've started adding a little bit of strong acid, to about right here before you approach the equivalence point, this is when you can use the Henderson-Hasselbalch equation to find the pH of the solution effectively. When you're actually right on the equivalence point, you're going to have to use an equilibrium expression to find the pH of the solution, as we learned how to do last unit. And another important thing to notice here is that when you begin the titration to the equivalence point, the halfway point is actually a special point where the pH equals the pKa. And this is called the half equivalence point. So that's a very important point to know. And then you can see that this graph here, if we talk about this, this is really just a mirror reflection. If you flipped this graph upside down, that's what this is. This is the titration of a weak acid, not a weak base, a weak acid by a strong base. So when we begin the titration, you can see that our pH is acidic because we started with just a jar of a jar of weak acid. And then as we start adding strong base to this weak acid, the pH is going to increase slowly at first, and then it will start increasing rapidly until the slope again reaches its maximum value at the equivalence point, where the moles of weak acid equal the moles of the strong base. And whenever you're titrating a weak acid by a strong base, the pH at the equivalence point will be greater than 7, okay? And again here, you have a half equivalence point where the pH equals the pKa. The third example I'd like to go through is a titration with a polyprotic acid. So we learned last unit that a polyprotic acid in general is an acid that can donate more than one proton. So I wrote up here the reaction of a general polyprotic acid. I put A for my acid subunit, and then it's attached to 2 protons which it can donate. So in its first proton donation, it's going to donate one of them to a generic base here, OH, and it will become HA minus. Now it only has 1 proton left. And I'm going to say that the first reaction here is associated with an equilibrium constant K1. And then in the second proton donation, HA is going to donate its second proton, becoming A2 minus, and then it donated its second proton to this generic base, making another water molecule. And the K associated with this reaction, I'm going to say, is K2. So if we were to titrate this polyprotic acid with a base, so we'll say our polyprotic acid is our titrand. So initially we're just going to have a jar full of polyprotic acid with no base in it. So the pH is going to start out very low, right? Because it's an acid. And then as we add more base, as we add more titrant, that's what the base is going to be, the pH is going to rise ever so slightly until it reaches this first equivalence point. And this is where we have donated all of the first proton. And halfway to this first equivalence point is the first half equivalence point, where the pH of the solution actually equals pK1 for that first proton donation reaction. Then in the second half equivalence point, pH is going to be equal to pK2, where it is halfway to completely donating all of its second protons from the HA to the A2 minus. So you can see here that this kind of looks like 2 titration curves stuck onto each other back to back. So that's all this is. So you can kind of see that a titration of a polyprotic acid is just like the titration of a monoprotic acid, except there are multiple curves with multiple equivalence points and multiple half equivalence points. Okay, and I'd also like to point out something that's very important for you to understand is that at this first half equivalence point, half of this H2A has been converted into HA minus. So at this point, the concentration of H2A would be equal to that of the HA minus. Then at the first equivalence point, all of the H2A has been converted into HA minus. So at this point, the solution contains all HA minus. Okay, then we're moving on to this second reaction for the second titration. And then pH equals pK2 at the second half equivalence point. And at that point, the solution is half HA minus and half A2 minus. Finally, we get to the second equivalence point, and at this point the solution is all A2 minus. So you can see here how pH equals pK1 and pH equals pK2 makes sense in terms of the Henderson-Hasselbalch equation. So remember, the Henderson-Hasselbalch equation says pH equals pKa plus log of the concentration of A minus over HA, right? So we know that at the half equivalence points, the reactant and the product that we're interested in are equal. So this is 1, and log of 1 we know is 0. So this whole term is 0, so pH equals pKa. So I hope that makes sense. Okay, so we've been talking a lot about how a solution's pH will change throughout a titration, but how do we actually monitor this pH change? Well, in modern times, we have these special digital devices called pH probes that you simply dip into the solution and it gives you a digital reading of the solution's pH in real time. But a cool way to measure the pH is with pH indicators, and these are actually special chemicals that change color at different pH levels. So right here I've got a general indicator that I abbreviated with I, and the requirements for a pH indicator is that it must exist in 2 different forms. One at a low pH, for example, and one at a high pH. And different indicators change forms at different pH levels. But the requirement stands that they must exist at different pH levels in different forms. And also, these 2 forms must have different and visible colors. So for example, maybe the HI here is red, and then the I minus is blue. So we know that if HI is present at a low pH, then it's going to be red. The solution will be red. But if the pH of the solution gets high enough, it will turn blue because the I- will predominate. And a third requirement is that the pKi of this reaction, Hi going to H plus I-, must be close to the equivalence point pH of your specific titration. So let's look at a couple examples down here. So in this example, I've got a titration where we're clearly starting at a pretty high pH. So we probably started with a base, and then we added some acid, and then we end up with an equivalence point at 4. So that means we must not have had a strong acid and a strong base. It must have been perhaps a weak base and a strong acid. And then you see another point here, the end point, and this is actually where the color changes. So if we're using an indicator, the color change is not going to be exactly at the equivalence point, and this is because the indicator itself will usually react with H plus or OH minus, thus skewing the actual pH of the solution when it changes color. So it can get us very close to the equivalence point, but not exactly. Okay, here's another titration where we started with a low pH, so we probably started with an acid, and then we had an equivalence point at 8. So that means this was probably a weak acid titrated by a strong base. And you can see here that if we used an indicator here, the color change would be after the equivalence point, and that's always how it goes. We can't get quite exactly to the equivalence point, but the end point is the point at which we change color when we use an indicator. So if we wanted to select an indicator for these two titrations, for this one, for example, we would want the indicator to change color somewhere between this range and this range, right? Preferably, maybe the indicator is red at pH of 5 and then blue at pH of 3. And at this point, we would see that, okay, when it changes from red to blue, we know the pH must have crossed its equivalence point because we selected the correct indicator for this titration, because we want the pKi of the indicator to be as close as possible to the equivalence point pH. So here's the equivalence point pH of this titration, 8. So we would want the indicator to change colors very close to 8. So we would want the pKi to be very close to 8. So hopefully that makes sense. Okay, now I'd like to walk us through a titration problem. So 20 milliliters of 0.2 molar HCl are added to 200 milliliters of 0.2 molar NH3. What is the final pH of the solution? So I want to remind us here that titrations are where we add together acids and bases. So at their core, titration problems are really just neutralization problems. And in this case, in particular, we have a weak base that is being titrated by a strong acid. So I drew up a little schematic here where you can see that our titrand is the weak base, NH3, and our titrant, the strong acid, is HCl. So we start out with just a beaker of NH3, a pure solution of NH3, and then we add in HCl and observe the pH change. And they want to know what the final pH is of the solution after we add in 20 milliliters of HCl. So you can actually do, this is a special case where when you use rice tables, you can use moles because everything in this beaker is going to be in the same solution volume. So you can actually assume that the volumes are going to cancel out. Molarity is moles per liter, and those liters are all going to be the same, so they'll cancel out. So here is the general titration curve that you'll see when you titrate a weak base with a strong acid. So up here, we're starting with just a pure solution of NH3, and then as we start adding HCl, we are going to ever so slightly decrease the pH of the mixture. And right here you can see that the NH3 solution is quite resistant to changes in pH. And that is because in these flat regions on a titration curve, you're actually in the ideal buffer zone. And if you look at what's going to happen when you add NH3 into the water, you have NH4 plus and NH3, a weak acid, and its conjugate base. That is the precise definition of a buffer system. So we actually have a buffer system in this initial range here. And if we keep adding HCl, we'll eventually get to the half equivalence point. And at this point, the moles of NH3 will be equal to the moles of NH4+. Actually, it's more accurate to look at this equation for the titration curve because this is when we're actually adding the titrant. So the moles of NH3 will be equal to the moles of NH4+ at the half equivalence point. And then finally at the equivalence point, the moles of NH3 will be equal to the moles of H+, and we will have completely neutralized our NH3. And then beyond that, we're simply adding excess H+ or HCl that is going to continue to lower the pH of the mixture. So the first step to this problem is to find the pH before adding the titrant. So in order to do this, we will set up a simple rice table for adding NH3 into an aqueous solution. And we know we started with 0.04 moles of NH3 because 0.2 molar times 0.2 molar times 0.2 liters is 0.04 moles. We didn't start with any NH4 because remember we started with a pure solution of NH3. And then we set up our rice table as you have seen before. And we know that the Kb of NH3 is 1.8 times 10 to the negative 5, so that is what our equilibrium constant will be. We set up our equilibrium expression, and we can ignore this minus x because the shortcut rule applies. In other words, 1.8 times 10 to the negative 5 times 100 is less than 0.04. We solve for x, and conveniently that is going to be our hydroxide concentration. So we then find our POH, which allows us to find our pH, and we see that we started with a pH of 10.93. So that is our pH of the initial mixture of NH3 and, I'm sorry, not a mixture, just our initial solution of NH3 before we added the titrant, HCl. So then the pH after we add the titrant, so we know HCl is going to break up into H+ and Cl-. The Cl- is not going to affect the pH, so we simply worry about the H+ interacting, rather neutralizing the NH3. So the NH3 will neutralize with the H+ to make NH4+, and we know we started out with 0.04 moles of NH3. We found that from the 0.2 times 0.2 liters. And then H+, well, we know we had 0.2 moles and 20 milliliters, so that's 0.2 times 0.02 liters, which is 0.004 moles. And then we didn't have any NH4 to begin with. So at this point we can say that we're going to lose the limiting reagent here, which is H+, 0.004 moles from each reagent, and we'll gain that in the products. And then you can see here in our equilibrium concentrations, we're left with 0.036 moles of NH3, no H+, and 0.004 moles of NH4+. So remember I said on a titration curve, if you're in this range, roughly this range, you can use the Henderson-Hasselbalch equation to determine the pH of the solution. So that range there and this range here. But if you're at the absolute end, so here we would have a pure solution of NH3, here we would have a pure solution of HCl, or at the equivalence point, at these 3 points, you have to use an equilibrium expression, like we did here because we were at this point, so we had to use an equilibrium expression. If we're in this range or this range, we can use the Henderson-Hasselbalch equation, which is a lot easier. So notice, at the equivalence point, we would have equal moles of NH3 and H+, right? Or NH3 and HCl, same thing. But we didn't have equal moles of those two things. We started out with 0.04 moles of NH3, but only 0.004 moles of H+. So we're not going to be near here, right? We don't even have half of the initial moles of NH3 and H+. We don't have 0.02. We don't even have close to that. So we probably really only got to about maybe here on the titration curve. We barely added any HCl at all. So we're in this range where we can use the Henderson-Hasselbalch equation. So we'll set up our rice table. We started out with these amounts that we found before, and we determined our equilibrium concentration. So now what we can do is set up our Henderson-Hasselbalch equation. So we know pKa equals pKb plus the log of A minus over HA. But before we get there, we have to determine the pKa of NH3, right? So we know pKa plus pKb is equal to 14. That's just an equation that we memorized from last unit. So that means pKa equals 14 minus pKb, and we can get the pKb. This was determined from taking the negative log of this. Remember, pKb is the negative log of Kb. So pKa is 9.25. So that's what's going to go into our Henderson-Hasselbalch equation. So pH equals 9.25 plus log of 0.036, which was our conjugate base here, and then 0.004, which was our weak acid. Remember the general setup for Henderson-Hasselbalch equations. And we'll get our final pH to be 10.21. So we started with a pH of 10.93 and only went down to 10.21. That's not a very significant change, especially for adding a strong acid like HCl. And that can be explained by this titration curve. So see how the slope is very small here. That means that we're just going to have a very slight change and very dull responsiveness to outside perturbations to our pH. In other words, this starts out in its buffer range, and a buffer would be most effective in that range. So this stuff is not easy. I know it's confusing, so please contact me with any questions or any problems you'd like me to work out on facebook.com/denovotutoring, and I hope this helped you guys out, and I'll see you in the next video.